Welcome to today's program. I'm Dr. Jim Daly of Astronomy for Change, your host, and we're pleased to bring you the Great Conjunction of 2020 live from the University of Exeter, England, the UK. The Great Conjunction 2020 live from the University of Exeter in the UK. Okay, we're just waiting on them. In the meanwhile, for those of you just joining us now, the conjunction is, what is a conjunction? A conjunction is when two major planets come together in the night sky, seemingly in the same position in the sky. Tomorrow, December 21st, which also happens to be the winter solstice this year, that will happen. And it won't happen again. And the planets will remain close together for a few days, up through the 23rd. Here, before they begin, so everybody has a sense of what this means, with stellarium. Fast forward. Now, since there's a 5-hour time delay between here and the UK, in the UK it's currently just not quite 4:15. They're going to be beginning momentarily. So tonight we have a waxing crescent moon. Sun is just setting, and for us here in the Northeast, the U.S. Northeast, Eastern Seaboard, this is what the sky will look like tonight at around. This is at 5:22 tonight, okay? And we have Jupiter, Saturn here, very close together in the night sky. It's going to make for quite a stunning event. We'll go right here and zoom in. Okay, if you have a pair of binoculars, this would be a breathtaking sight. With Saturn right here. We're going to hear them go live. As soon as they go live, we'll switch back to them live from Exeter. University of Exeter. Yesterday we attempted this. There was inclement weather in the United Kingdom, in that particular part of England, and so they postponed it again for today. Technically, tomorrow is the day when these two planets will be together, the closest point together in the night sky. Now, I should add also that this won't happen again. A conjunction of this, like this, you will have to wait 60 years. To the year 2080 to see it again just like this. So if you have an opportunity to check it out, I would recommend doing so because it won't happen again for another 60 years, the year 2080. Okay, so again, if you're just joining us, we're going to be going live to the University of Exeter momentarily when they start their live stream. And this is the night sky tonight here, Eastern Seaboard. And it's been some discussion, some of you may have seen on the news, some news reports of the Christmas star. What's that all about? It's important to note that the Christmas star is thought to have been not a star actually, but more as a metaphor for something like a conjunction, where it was meaningful to the people of the day, the Jewish people of the day, in the year 7 BC, in the spring of 7 BC, that a triple conjunction of Mars, Jupiter, and Saturn occurred in the constellation of Pisces. And we're going to take a look at that now. We can do that with stellarium, but for now, this is what it would have looked like using stellarium. I reproduced this using stellarium. The spring was 7 BC, February 4th, 7 BC, was a triple conjunction of Mars, Jupiter, and Saturn in the constellation of Pisces, right there, okay? Although it happened during the day, the wise men, the three wise men as they're referred to in the Bible, would have known about it. And even though they couldn't see it visually, they would know it occurred because they were astronomers, astrologers, they were wise men, very learned, educated men. And they would know that this was happening. And hence they describe this as the Christmas star. Now that's some would suggest that that's the Christmas star, and it's poignant to understand right now that this is happening this week on the 21st. Actually goes out to the 23rd. They'll be very close together through the 23rd of December. And again, when the live stream finishes, if those of you like to stay, we're going to go back and take another look at this with stellarium to see how long this will continue. We can do that with stellarium. Okay, it's poignant to remember that this has happening during the Christmas season. I think it's a nice way to close out the year 2020, I think. Try to close it out on a positive note. Okay, so let's check out to see where they are. Okay, they still haven't started yet. This is the web portal, the Great Conjunction 2020.
How's it looking over there?
Are they starting now?
Hello, everybody. Okay, welcome back. Let's hope, well, at least those of you who joined us yesterday, let's hope we have a bit more luck tonight. We've got some excellent pictures to show you from last night, though, after the rain and cloud cleared away. So you can definitely hold on to those regardless of what happens this evening. But we have a mostly blue sky at the moment. So let's hope that we keep that over the next hour and a half, and we can show you some of these live pictures. Stephen, do you want to introduce yourself?
Hello everyone, I'm Steven Rieder. I'm a researcher here and also a hobby astronomer. So we're trying to see Jupiter and Saturn with my telescope here. At the moment I can't see them yet, it's just a little bit too close to sunset. But in the next 5 or 10 minutes we hope that we can see them, and it's blue sky as Matthew said, so we'll have some luck today. We expect to, at least. Back to you.
Thank you for that, Matthew and Stephen. We really hope we get a good view tonight. We are also so lucky to be joined by a whole panel of astrophysics experts from the University of Exeter, ready to answer your questions. They'll all introduce themselves now. So firstly, Dr. Jenny Hatchell, who's a lecturer in astrophysics.
Hi, I'm Jenny Hatchell, and as well as lecturing, I specialised in the early stages of star formation. Today I'll be showing you a model that you can try at home to see why we're observing a great conjunction today and why we don't see them very often. Back to you.
Lovely, thanks Jenny. So thanks to everyone who's sent their questions in advance. We'll put lots of them to our experts tonight, and we've got Adrienne monitoring your comments on YouTube as well, so do get in touch. Now I'd like to introduce Dr. Sebastian Kreit, a lecturer in astrophysics.
Hi everyone, my name is Sebastian. I'm a lecturer here at the University of Exeter, where most of my research deals with the formation of planets and planetary systems. I'm excited to be back after yesterday, and I look forward to answering any questions you may have. Back to you.
Thanks. Stephen Thompson, a lecturer in the Maths department.
Hi, thanks Alice. Yeah, my name is Dr. Stephen Thompson, and I'm, as you say, a lecturer in the Maths department here in Exeter, and my research is focused on the weather and climate on giant planets like Jupiter and Saturn, and also terrestrial planets like Earth and Mars. I focused mostly on the maths behind the weather on these planets and what lessons we can learn from our solar system neighbours to help us understand Earth better. I'm really excited to be here with you all tonight, and I'm looking forward to answering your questions.
Federica Roscigno, who is she's a PhD student in the astrophysics group. So Fede, if you can just introduce yourself, that'd be great.
Hi everyone, I'm Federica, and I'm just starting my PhD here at Exeter University. I'm currently in exoplanetology, which means I focus on studying and better understanding stellar activity to allow for the detection of small Earth-like planets. I'll be around to answer some of the questions, and in particular to get the younger crowd interested in astronomy.
The joy. So I will just introduce Nathan on his behalf. So Nathan is Associate Professor of Astrophysics and Planetary Climates, and he does some fantastic research in collaboration with the Metaspheres, looking at the atmospheres on other planets. And we're going to talk to him about some questions you've had about the specific conditions on those planets later. Brilliant. So hopefully you'll all get to see and hear him in a bit. So I think now that we've introduced everyone, we'll check back in with Matthew and Stephen and see how you're doing.
Okay, that was absolutely excellent timing there, Alice, because Stephen's just found Jupiter and Saturn, and he's just aligned the telescope on, let me see, both of them. So Sam, if you can switch to Stephen's live feed right now, we can show them the first live image of Jupiter and Saturn together. They're going to be a little faint, obviously, because Because what? Because it's still very light here, as you can see behind me. Sam, I think my image. Yes, exactly. That's right. So get rid of my image. Yeah. So okay. So what you can see here on the, I hope it's the left. Is it the left? Is Jupiter down the bottom, and then the fainter object, which is on its side actually. So it's like Saturn tilted, so its rings are sort of vertical. That is Saturn. So Stephen's just said that he's going to rotate the camera later. Yeah, so these are already about 1/3 closer than they were last night. As I said, you'll see some of the footage that we got from last night later. The footage that you'll see later, Jupiter and Saturn are really on the extremes of the CCD from last night, and here they're well placed inside, so we've got plenty of space around them. So is it possible to zoom? Okay, so Stephen's just going to try and zoom in on Saturn itself, and we might be able to give you the first close-up view of the rings, so just stand by. Okay, so you can see Saturn moving. Okay, so at the moment, you're seeing them 1/3 of the moon's diameter apart. Okay, so here's Stephen's just zooming in. Okay, so get it the way you like it, Stephen, and just leave it there for a little bit. So yeah, what you've already just seen is an image of Jupiter and Saturn closer together than they have been since 1623. Okay, so although the closest point of this great conjunction is going to be in about exactly 24 hours and 10 minutes from now, already they are closer than 9.5 arc minutes. And that means that they're now closer than the 1961 conjunction, which some of you may have seen. The 1961 conjunction was a little bit wider than this. I think it was about 11 arc minutes. So last night, they were further apart than 11 arc minutes. And so the last time they would have been seen that close was in 1961. But tonight, we actually go all the way back to 1623. They haven't been this close since 1623. And if any of you know about the 1623 conjunction, maybe you watched my video on the history of great conjunctions or something else, you'll know that the 1623 conjunction was actually very close to the sun. So it was very difficult to observe, and there's actually no records that anyone observed it. And so if we go back to the last time they were observed to be this close, that was 60 years before the 1623 conjunction, so 1563. And so you're probably looking now at what hasn't been seen. Well, you're looking through a telescope, so there was no telescope in 1563. Hadn't been invented yet. But you're looking at Jupiter and Saturn, which this close, they probably haven't been seen since 1563. So that's 457 years ago. So nearly half a millennium. So this really is a sight. And I guess the other thing to say is, you know, if you can see them over the next 2 days, so either tonight, tomorrow night, or Tuesday night, then on each of those nights, at least in the UK, it depends exactly where you are in the time zones, but any one of those 3 nights, if you can see them then the last time they've been seen this close will probably be 457 years ago. So really do make sure you see them with your own eyes, with binoculars, with a telescope, whatever you've got available. Okay, how are we going? You've just zoomed back out again, have you? Yep. So this should come on the screen in a second. We have a few seconds delay between what Stephen does here and what appears on the YouTube screen. Yep, there we go. Okay, so yeah, so anyway, that's your first live view of Jupiter and Saturn tonight. Right, so shall we switch back to the studio, as it were? Yeah, we'll talk to you again in a few minutes.
So that looks good, looking good.
Brilliant. Thank you very much, Matthew and Stephen. That was looking so cool. So yeah, Matthew prepared a video which explains what we're hoping to see tonight, and also how you can see the Great Conjunction without a telescope. So we'll go to that now.
Those of you who are just joining us, this
Jupiter and
is
Saturn looks
Dr.
like
Jim
over the
Daly.
past 2 weeks.
We're live from the University of
Stephen
Exeter in the
Reeder and
UK.
myself, Matthew Bate, have captured photos and videos on clear nights, some of which I'm going to show you now. This photo was taken with a camera on December the 8th. You can see Saturn in the top left, and Jupiter and the 4 Galilean moons that were discovered by Galileo in the bottom right. Jupiter and Saturn were approximately 3 lunar diameters apart at the time. Tonight they'll be 9 times closer, just 1/3 of the diameter of the moon apart. Here I zoom up. The telescope has a focal length more than 3 times longer than my camera lens, so it provides much higher resolution images. This allows Saturn's rings to be seen, although we're still dependent on the atmosphere being relatively still, otherwise it distorts the image. The fact that the Great Conjunction is only visible near the horizon means we're looking through a lot of atmosphere, so you shouldn't expect very sharp images of Jupiter and Saturn themselves tonight. Regardless of what we see tonight, don't forget to try to see the Great Conjunction yourself, simply using your eyes. I took this photo over Exeter on December 12th. Jupiter and Saturn were about 4 times further apart than they will be tonight. This is what Saturn looked like on December the 12th. Note that the upper part looks blue, while the lower part looks red. This is because blue light is refracted more than red light as it passes through the atmosphere. This effect gets stronger as Saturn gets closer to the horizon, so you may see it again tonight. On December 15th, Jupiter was noticeably closer to Saturn, and again you could see all 4 Galilean moons, but in a different order than they were on December the 8th. Here I've combined 2 different photos with different exposures to allow you to see Saturn's yellow colour and the 4 Galilean moons at the same time. Here's another photo of Saturn and Jupiter over Exeter, this time on December the 14th. You'll notice Saturn is significantly fainter than Jupiter. I think it makes a lovely Christmas photo. So if it's clear tonight, what might we expect to see? Jupiter and Saturn are now much closer than the photos you've just seen. Hopefully we'll be able to see Saturn's rings and all 4 of the Galilean moons of Jupiter simultaneously. You'll also notice there's a star close to Callisto. That's Jupiter's 2nd largest moon. We may also be able to see some of Saturn's moons, Saturn's largest moon Titan, and maybe some of the fainter ones. Jupiter and Saturn will be at their closest to each other just 24 hours from now, with about 2/3 of the separation they have tonight. We don't have long to observe Jupiter and Saturn tonight. Even if the sky is clear, they're slowly sinking towards the horizon and will set around 6:15 p.m. Let's hope for clear skies tonight.
Thanks for that brilliant video, Matthew. And we've just heard that there's going to be something, that we should be able to see something exciting at the telescope now, so we're going to go straight back to Matthew and Stephen.
Okay, so what you're seeing now is, again, Jupiter and Saturn. I think Stephen has rotated the image since we last saw it. Hang on a minute here. So if you look very carefully, so they're still quite faint, but on the right of Jupiter, just about 1 Jupiter diameter away from Jupiter, is either Europa or Io, one of the closer 2 moons, which we'll hopefully see tonight. And then when you go on the left-hand side, we're talking something like about a third of the distance between Jupiter and Saturn, but lower down, much lower down than Saturn, then you should see Ganymede. So Ganymede is the largest moon of Jupiter, and in fact, it's the largest moon in the solar system. It's also slightly bigger than the planet Mercury. Okay, so this is a very large moon. And then if you keep going out, if you've managed to see Ganymede, if you go out again, following the line from Jupiter to Ganymede, but just keep going about 2/3 of the distance again, then you'll just see Callisto. All right, so Callisto is the second largest moon of Jupiter. It's also the most cratered object in the solar system. So it has a very old surface. The surface hasn't been modified for billions of years, we think. And so it has a lot of craters from when the solar system was still settling down, asteroids, comets plowing into it. So that's Callisto, second largest moon of Jupiter, and the most distant in terms of the 4 Galilean moons, which we'll hopefully see tonight. So again, they're a little bit faint. There's 2 reasons for that. The first is that although the sky is clear, it is a little bit hazier than last night. The nice thing about the rain last night was that it cleared out the atmosphere absolutely wonderfully. And so when the cloud did move away, we did actually manage to get some really good views, which you'll see later. So we've got a little bit of haze, and of course it's still just getting dark here, right? So this is going to look a lot better in probably another 15 minutes, certainly another half hour. So just stick with us. Hopefully you like what you see. You can see the rings of Saturn here quite clearly now. You can even see the gap between Saturn and the rings themselves. Saturn is 60,000 kilometers in radius, and the rings extend down to 7,000 kilometers above Saturn's surface. So they really do get quite close to within about 15% or so of Saturn's radius overall. But then the rings, in terms of their outer size, they're actually more than twice as large as Saturn itself. So that's why you can clearly see the very oval shape here. And indeed, as I said, the atmosphere is just stable enough tonight to be able to see the gap between them. And again, hopefully that will improve as the evening goes on. Alice was saying maybe I should talk a little bit about the telescope as well. Would you like me to do that now, perhaps? If you want me to do that, Sam, then you can switch back to my webcam. Well, actually, do we want to do that? Well, I guess we will talk about the telescope here a little bit. Okay, so this is for the Americans, and I know there were some Americans that joined us last night. Hopefully they'll come back again tonight. So this is an 8-inch diameter telescope. That's the main mirror. For the Europeans among us, obviously Stephen is a European, so we better give that measurement as well, and that's 200 millimeters diameter.
20 centimeters.
So we're talking something like very big. Okay, so back here, yep. So we've got, this is a Newtonian telescope, so it's quite simple in terms of telescopes. There's only the big main mirror at the back here, and then that takes in the light, passes it forwards to near the front end of the telescope, where there's a little secondary mirror, which is at a 45-degree angle. And so the light from the main mirror gets shot out the side of the telescope, which is where you can see Stephen's camera here, which is a little red camera, and that's a CCD camera, a special one that Stephen bought just for particularly planetary objects. It's relatively small field of view, which is why we could only get both planets in the field of view last night. That was the first time. We hadn't been able to do that on earlier nights. We had to use a normal camera. But yeah, so that's working really well. It's on an equatorial mount. So you can see the mount here. there are basically two sort of mounts in astronomy. There's the equatorial type mount, and there's the alt-azimuth, or what else is it called? Anyway, so the simple mount, if you like, just goes sort of left and right and up and down. But the equatorial mount, this is aligned with the either North Celestial Pole if you're a Northern Hemisphere person, or I'm originally a New Zealander, so we used to align things with the South Celestial Pole. And so what that means then is the telescope can track around on the stars very easily. It just naturally follows the movement of the stars and planets across the sky as the Earth rotates. So we've got the equatorial mount, which makes Stephen's life a heck of a lot easier because he doesn't have to spend a lot of time following objects. And that's about it, I think. Yeah, so maybe, okay, so yeah, we've switched back to the live stream now. You can see Ganymede quite clearly now. As I said, to the left, about roughly a third of the distance between Jupiter and Saturn away from Jupiter, but lower down, closer to Jupiter. So hopefully you can make that out. And these will just hopefully get brighter as the evening wears on. So I think we'll switch back to...
You can see it. The simulation between stellarium and the live view is quite good.
Questions that can be answered from people who have written in. But yeah, stay tuned.
Great. That's looking so cool. Thank you so much, Matthew. So yeah, if you've just joined us, we are live streaming the Great Conjunction, the closest that Jupiter and Saturn have appeared in the sky for 400 years. But how do conjunctions work? So Dr. Jenny Hatchell has made a great demo that you can try at home to better understand what's going on.
How do we get a great conjunction? The planets in the solar system orbit around the Sun. For example, the Earth takes 1 year to travel around the Sun. Jupiter is about 5 times further away from the Sun than the Earth, and Saturn about 10 times. When 2 other planets line up in a straight line from the Earth, that's called a conjunction. When those 2 planets are Jupiter and Saturn, it's called a great conjunction.
Great. So if there are any children watching, why not try that at home? Jenny, we have a question from Ian. Though they look close to each other, how far apart are they? And Robert would like to know which one is moving fastest in its orbit.
Yes, okay, so although the planets look really close together on the sky, actually they're still really far apart. And we can work that out starting out with the distance between the Sun and the Earth. So this distance is a whopping 150 million kilometers. And because we use that distance a lot in astronomy, it has a special name. It's called 1 astronomical unit. So if we go to Jupiter, Jupiter is 5 astronomical units away from the Sun, a little bit more than actually, about 5.2. And Saturn is at 9.6 astronomical units from the Sun. So the distance between Jupiter and Saturn is about 4.4 astronomical units. In kilometers, that's 655 million kilometers. And the rule with the planets is the ones closest to the Sun move fastest. So Jupiter is moving much faster than Saturn is. Back to you, Alice.
Lovely, thanks, Jenny. Another one, so Jennifer and Carl both want to know if Jupiter will ever actually pass directly in front of Saturn and eclipse it.
So what you're asking is if this can ever happen. For that to happen, the planets have to be closer together, over 10 times closer together than we're seeing them at the moment. Now, if you go back to the year 372, they were separated by about 1/3 of the separation that they will have tomorrow. And so that's the closest that they've been in the last 2,000 years. But that's still not close enough for Jupiter to eclipse Saturn. The American astronomer Pat Hartigan has worked out that Jupiter may have eclipsed Saturn. But you would have to go back 9,000 years to the year 6856 BC. Or if you go forwards 5,500 years from now, Jupiter may have eclipsed Saturn in the year 7541. That's a little bit uncertain because it's hard to calculate the orbits really accurately so far in the past and so far ahead. But it is possible, it just doesn't happen very often. Back to you, Alice.
Great, thank you. So we've got another nice demonstration to show you now that Jenny set up earlier to help explain a bit more about how conjunctions work.
When will we next get a great conjunction? Well, the Earth orbits the Sun in 1 year, but Jupiter takes 12 years and Saturn 30. That means each time the Earth goes around the Sun once, Jupiter just moves 1/12 of an orbit. A 12th of an orbit, to get a 12th of an orbit, we can divide our orbit into 4, that's quarters, and then each of those quarters into 3 parts, like a clock face. So in a year, the Earth goes around once, Jupiter moves 1/12 of an orbit, and Saturn just 1/30. In another year, the Earth goes around once more, Jupiter moves another 12th, and Saturn another 30th. You can see that these planets are no longer in a straight line, and we no longer have a conjunction. As Jupiter continues to move on and Saturn continues to move on, you can see that Jupiter is gaining on Saturn. So eventually, Jupiter is going to lap Saturn, but not until Jupiter has gone 1.5 rotations and Saturn has gone a little more than halfway. At that point, the planets will once again align, and we will once again get a great conjunction. That isn't going to happen for another 20 years until 2040. And even then, the planets will not be as close together as they are this year. They won't be as close together again until 2080, in 60 years' time.
Thanks so much, Jenny, for those really helpful demonstrations. If you've just joined us, we are celebrating the Great Conjunction this evening, and we are live streaming from the University of Exeter and co-hosting with the Exeter Science Centre. So we've got a question come in from Harry, age 8 in Barnstable, and he says, how far apart will Jupiter and Saturn actually be on the sky? How far apart will they look? So we're going to check back in with Matthew and Stephen at the telescope on the roof of the physics department at the University of Exeter to find out.
Okay, so thanks for the question, Harry. Sorry we didn't get to answer it last night. We were a little bit more concerned about the rain. So yeah, you can see again our live image of Jupiter and Saturn here. As I said, at the moment, they are about 1/3 of the diameter of the moon away from each other. And over the next 24 hours, in fact, so 11 minutes less than 24 hours now, they will reach their closest approach to each other this year, and then they'll be 1/5 of the moon's diameter apart. That will be about 6 arc minutes. Now, you probably don't know what an arc minute is, but you might know that if you take a full circle, that can be divided up into 360 degrees, all right? And then if you take one of those degrees and divide that again by 60, that is 1 minute of arc. This is a measurement that astronomers use all the time. If you divide 1 minute of arc again by another 60, you get down to 1 second of arc. So it's a little bit like time in the sense you've got seconds and minutes, but then you have degrees rather than hours. And in fact, 360 degrees, because there's 24 hours in a day, that means that things rotate in the sky, for example, at least by 15 degrees every hour, which is why when I was referring to the telescope before, we need this equatorial mount because everything's moving at the rate of 15 degrees per hour, and if we just have a static telescope, they very quickly drift out of the field of view. As you can see, they're staying rock solid in Stephen's telescope camera at the moment, and that's because they're continuously being tracked. Anyway, so the answer to your question is, yeah, that currently they're 1/3 of the diameter of the full moon apart. You're in Barnstable now, I believe. I'd really encourage you, to be honest, to go outside right now and actually maybe give it another half hour, but do try and see them tonight just with your eyes. They're going to be quite the sight. Still a little bit bright at the moment, despite what we're seeing from the telescope here. The other thing, just while we're looking at the telescope image here, notice that Saturn is definitely yellow now. And so Saturn is a very yellow type planet. You can't quite see the bands on Jupiter, I don't think, at the moment, can we, Stephen? So Stephen's just going to play around with the sensitivity on the CCD camera here, so we can turn that up and down. So you'll see Saturn fade away a bit here, but we're just going to see whether we can show you any bands on from Jupiter's atmosphere. So Jupiter rotates with a period of about 10 hours. It's the fastest rotating planet in the solar system, and it's got very high speed winds. I think it's something like 400 miles an hour that the winds circle around the planet. These don't develop clouds quite like on Earth, which is sort of, you know, puffy type things. Instead, you tend to have, at least on the global scales of Jupiter, it tends to break the clouds into bands with different colors. Is it possible to zoom in on Jupiter a bit, Stephen? Let's just see how you can see that Jupiter's wobbling around a little bit. That is going to be a problem throughout the night, because as Jupiter and Saturn get further down towards the horizon, the light is passing through more and more atmosphere, and there's a little bit of wind, there's a little bit of turbulence. That's going to make the planets wobble around a little bit. But let's just see whether we can see some of the atmospheric bands or not. So you might have to use your imagination a little bit. So we're going to show you a video later with some of Stephen's images from last night, and what he's done with those is take a whole series of images from the video stream and stack them together, and that gets rid of some of this atmospheric distortion which you see just in the live video here. So I think I can make out maybe one band, but it's a little bit wobbly at the moment. Anyway, so hopefully things will get a little bit calmer as the evening goes on. We're still staying clear here at the moment, and so I think we will pass back to the studio again. So I hope that answers your question, Harry. Very good question, and we'll answer some more later. Okay, back to you. Who are we going back to now? Alice or Natalie?
Thanks very much, Matthew. That was fantastic, and it's great to see these amazing planets starting to become visible. So we're celebrating the great conjunction of Jupiter and Saturn this evening. So let's find out a little bit more about the origins of these amazing gas giants.
Even though they will appear close from our point of view, in reality the two giant planets will still be pretty far apart. Jupiter and Saturn orbit the Sun on near circular orbits, at distances of roughly 5 and 9.5 astronomical units respectively. In such a configuration, the closest approach between the two planets is about 4.5 astronomical units, or 4.5 times the distance between the Sun and the Earth. It wasn't always like that, however. When our Sun was born, a little over 4.5 billion years ago, it was surrounded by a massive dense cloud of gas and fine dust. The planets of the solar system all formed from the raw materials present in this solar nebula. The cores of the giant planets formed first, within a couple of million years at most, and this allowed them to capture and hold on to their massive hydrogen and helium-dominated atmospheres until today. By studying the orbits and physical properties of the planets, as well as those of the comets, asteroids and Kuiper Belt objects, astronomers and planetary scientists try to piece together more and more information about this messy initial planetary formation phase. Two theories that have been put forward and developed recently, and prominently feature both Jupiter and Saturn, are the Nice model, named after the city in southern France where it was developed, and the Grand Tack model, named after the sailing manoeuvre. The Nice model addresses the period just after the accretion of the giant planets was completed. It argues that the solar system's four outer planets, Jupiter, Saturn, Uranus and Neptune, were formed in a more compact configuration, surrounded by a swarm of smaller, asteroid or comet-sized bodies. This computer simulation shows how the orbits of the outer planets, shown as circles, interacted with the leftover planetesimals, shown as green dots. Over hundreds of millions of years, the combined effect of many small gravitational interactions with these planetesimals resulted in the planets themselves slowly moving outwards. This led to an instability and final orbits of the planets that were considerably further from the Sun. The Grand Tack model instead describes an earlier phase, when the cores of the giant planets were still surrounded by a dense gaseous nebula, and the terrestrial planets had not yet formed. Hydrodynamical simulations show that a solitary Jupiter-mass planet embedded in a disk will migrate inwards due to the interactions with the surrounding gas. Left alone, Jupiter would likely have ploughed through the inner solar system, disrupting the formation of the inner rocky planets. The Grand Tack model argues that it was actually Saturn that prevented this from happening. Forming slightly later and further out, Saturn also migrated inwards, slowly catching up with Jupiter. The two planets eventually became locked in an orbital resonance, close to where the current orbit of Mars is located, which caused them to reverse course and move outwards together. This Grand Tack manoeuvre played a big role in shaping the inner solar system, and is thought to be responsible for the relatively small mass of Mars, and for aiding the delivery of water-rich asteroids to the forming Earth. Together, the Nice and the Grand Tack models paint a highly dynamic picture of the early solar system, and one in which Jupiter and Saturn had a profound influence on the evolution of the terrestrial planets.
Fantastic. So thanks so much to Sebastian, our expert in planetary formation, for preparing that video for us. Now we're going to go back to Matthew and Stephen quickly to check out the view, because we can see some clouds approaching. Matthew, over to you.
Okay, hello again. Yeah, we've got two developments here. One's great and the other's not quite so great. So we are going to lose probably the view at least for a few minutes. We've got a low cloud which is coming across.
We don't have a few minutes left.
How long that's going to take to get to us. So we thought we'd switch back to the...
We have about probably 30 minutes left.
Telescope now while we're still able to. And...
Right now, it's
okay, so
5 p.m., almost 5 p.m.
What you should be able to see at the moment, Sam, is it possible to
1 minute to 5.
Stream me and just have the view, because otherwise...
Right there.
Okay, fine. Thanks a lot, Sam.
So that's what they're seeing over there right now.
Otherwise, I can't see the image very large. Okay, so can you make that a little bit brighter, Sam? Sorry, too many people whose names start with S. Okay, fine. Okay, so what we've got now, though, is we've got Jupiter and the moons, which ideally are a little bit brighter. If the okay, I think, oh, beautiful. Okay, fine. Okay, so hopefully what you're seeing now is Jupiter and Saturn. Okay, Jupiter's the really bright round thing, Saturn's the oblong bright thing. So what we've done is we've switched to very high sensitivity here to try and see the moons as much as we can. All right, and so what you can see is if you look very close to Jupiter on the right, you will see the moon that we saw before, which is distinct from Jupiter itself. That is Europa. All right, so that's the smallest of the 4 Galilean satellites of Jupiter. And then you'll see, if you look at the edge of Jupiter, just next to Europa, you'll see a bulge. So that is Io. That's the most volcanically active moon in the solar system. And it's the closest of the 4 Galilean satellites to Jupiter. It orbits Jupiter in just 1.8 days. So every day you come back and look at Jupiter, Io will be in a completely different place. Going to the the left-hand side, you can clearly see Ganymede now. That's the one that's about a third of the distance between Jupiter and Saturn away from Jupiter. And then again, going out in a line, you can see Callisto is the next moon that you come to. That's, as I mentioned before, the most cratered object in the solar system. And then you'll see another object a little bit further away from Jupiter than Callisto. That's actually a star. Okay, so
That's why the Great Conjunction is only visible for about 1.5 hours after sunset, in the twilight and early evening before Jupiter and Saturn also set.
See what this looks like if we were to take a vantage point beyond the Earth's orbit and look out at our solar system. What would we see? So I set the date here for the 14th of December. And if we find the Earth right here, okay, and we're going to position our viewing angle such that Saturn and Jupiter are lined up. When they're lined up like this, we call that a conjunction. As seen from the Earth, we align ourselves with the plane of the solar system like this. Okay, this is, and we're here on the Earth, vantage point of the Earth. We're looking out into space. Okay, right here in Stellarium. This is what it looks like. Okay, now as the two planets get closer and closer together, as they apparently in the sky, they're going to come together and almost seem to merge as one. Okay, so let's run this forward and see what happens on the 21st. You can see them right here, even on the 14th, which is a week before. It looks quite spectacular. So let's run it forward. Speed it up just a bit. We're at the 16th. You notice there's not much change from one day to the next here. Okay, the 19th, 20th, and the 21st. We'll stop it there. We'll zoom in. Okay, zoom into the Earth, center on the Earth, zoom in. Just leave it like that. Looking across the solar system with the sun here, sun to the east, looking directly across the solar system, and we witness Jupiter and Saturn in conjunction, and this is what it looks like in the night sky.
The 1623 Great Conjunction was even closer to the Sun. Saturn was just 13 degrees from the Sun, so it would have set only about 50 minutes after sunset. And of course, it's very dangerous to point a telescope near the Sun. Don't try to observe Jupiter and Saturn until after the sun has set. There are no records of Galileo or anyone else observing the 1623 Great Conjunction through a telescope and seeing Jupiter and Saturn at the same time. The exciting thing about this is that if you observe Jupiter and Saturn simultaneously through a telescope this year, you, along with many others in 2020, will probably be the first in human history to see this sight. Finally, some people have suggested that the star that led the Magi, or wise men, to find the child Jesus Christ may have been the Great Conjunction of 7 BC.
The Christmas star is thought to have been not a star actually, but more as a metaphor for something like a conjunction, where it was meaningful to the people of the day, the Jewish people of the day, in the year 7 BC, in the spring of 7 BC, that a triple conjunction of Mars, Jupiter, and Saturn occurred in the constellation of Pisces. And we're going to take a look at that now. We can do that with stellarium, but for now, this is what it would have looked like using stellarium. I reproduced this using stellarium. The spring was 7 BC. February 4th, 7 BC, was a triple conjunction of Mars, Jupiter, and Saturn in the constellation of Pisces. Right there. Okay? Although it happened during the day, the wise men, the three wise men as they're referred to in the Bible, would have known about it. And even though they couldn't see it visually, they would know it occurred because they were astronomers, astrologers, they were wise men, very learned, educated men. And they would know that this was happening. And hence they describe this as the Christmas star. Now that's some would suggest that that's the Christmas star, and it's poignant to know, to understand right now, that this is happening this week on the 21st. Actually goes out to the 23rd. They'll be very close together through the 23rd of December. And again, when the live stream finishes, if those of you like to stay, we're going to go back and take another look at this with stellarium to see how long this will continue. We can do that with stellarium. Okay, it's poignant to remember that this is happening during the Christmas season. I think it's a nice way to close out the year 2020, I think. Try to close it out on a positive note. Okay, so let's check.
This conjunction was a triple Great Conjunction with 3 close passes within 7 months. This would have given the Magi time to travel from their home country to Jerusalem and then on to Bethlehem. There are many other suggestions for what the star may have been, but since the 2020 Great Conjunction happens to occur just before Christmas, it's something you might like to ponder as you observe Jupiter and Saturn this year.
I'm speaking now. Fantastic. So we've got another update from the telescope, so I'm going to pass over straight to Matthew.
Okay, so we're back at the telescope now. So Stephen has again boosted the gain, and I'm getting a speaker view of Natalie still. Don't know whether you can do anything about that, Sam. But what you can hopefully see again is Europa again to the right of Jupiter. Io very close to the edge of Jupiter between Europa and Jupiter. Then Ganymede and Callisto out to the left. And with a bit of luck, you might see Titan a little bit more easily next to Saturn. Thanks, Sam. So Titan is at about the 2 o'clock position, about 3 times the diameter of Saturn's rings away from Saturn to the right. So it's just a sort of faint smudge probably that you can see. So that is the largest moon of Saturn. Sam, if you could put up the image of Titan and Rhea. So this image was taken by one of the space probes that's been sent out to
the Cassini,
Saturn.
Cassini-Huygens mission to Saturn.
Cassini. What you see here is Titan is the big orange moon here, the crescent. Titan is an amazing place because it's the only place in the solar system other than Earth known to have liquid lakes and rain. Okay, so, but this is not water on Titan. So Titan's surface temperature is minus 180 degrees C. And so instead of water falling as rain, this is methane and ethane in the lakes. And so the other thing is, in a way, the atmosphere is very similar to Earth. Okay, it's an awful lot colder, but Titan's atmosphere is mostly made of nitrogen, the same as Earth. So Earth's atmosphere is, I think, about 78% nitrogen. Titan's atmosphere is 97% nitrogen, and then about 3% methane. And it's the methane that forms clouds and rains and fills up lakes. And so some of the lakes on Titan are quite shallow. We know from radar measurements that some are just a few meters deep. But there are some lakes where we can't measure the depth, which must mean that they're over 200 meters deep. So just think about lakes of hydrocarbons, things like methane and ethane on Titan. The other thing is, I said it was sort of Earth-like in a way, so it's a very nitrogen-rich atmosphere. The atmospheric pressure is also very high. It's about 50% higher than Earth's atmospheric pressure. So that means if we were out on Titan, obviously we'd have to protect ourselves from the cold, but the atmospheric pressure would actually be pretty much fine for us to walk around in. So that's quite interesting. Rhea is the second largest moon of Titan. We're not able to see that at the moment, but Stephen got some images which you'll see later of Rhea and Titan, and also two other of Saturn's moons, Dione and Tethys, which you'll see later in the material that we prepared from last night's images. So Rhea, as you can see, doesn't have an atmosphere. You can see a cratered surface there, a little bit like the moon. Titan is the only moon in the solar system which has a substantial atmosphere. Right, what do we want to do now, Stephen? Shall we? So we've got some high altitude cloud coming, and so we want to try and give you as much of a view of Jupiter and Saturn live as we can. So essentially, we're just going to keep talking about the live image as much as we can before this cloud comes across. So maybe could we zoom up on Saturn and maybe reduce the gain and have a good look at its rings? That might be a nice thing to do. Okay, so there's a slight delay coming through the feed, but what you should see in a second is a zoomed in view of Saturn. Okay, so here it's coming. All right, and so, yeah, excellent. Okay, so again, a little bit harder to see now because Saturn and Jupiter are getting a little bit lower in the sky. There's more atmosphere to look through, but again, you can see clearly the round disk of Saturn, and then what Galileo referred to as ears on the side of Saturn. So when Galileo first looked at Saturn through his telescope, he'd looked at Jupiter first, and he'd discovered some of the moons of Jupiter, and then he turned his telescope to look at Saturn, and he realized it was an oblong shape, and he wasn't sure what these ears sticking out from Saturn were, whether they were two moons, one on either side of the planet, which were just very, very close. It wasn't until Christian Huygens in 1655, I think, first proposed that these ears were in fact not ears, but they were a disk around Jupiter. Sorry, around Saturn. Thank you. So yeah, and so that's a nice image there of Saturn. Right, shall we zoom out again? Yeah, Okay, let's just look at this view a little bit longer. Okay, so we'll zoom back out again. Okay, so I can talk a little bit about Saturn's rings actually, while you're looking at, yeah, maybe you can boost up the gain a little bit again. So Saturn's rings are mostly made of water ice, and are made of particles which range from meters in size right down to microns. So a micron is about a millionth of a meter, a thousandth of a millimeter. So from very small particles right up to sort of meter-sized objects. They're very thin. They're thought to be perhaps only something like 10 meters in thickness. And yet, as I said before, they're obviously very broad. They extend from 7,000 kilometers above the top of Saturn's atmosphere out to 80,000 kilometers from Saturn's equator. So they're really amazingly broad and yet quite thin. It's estimated, again, Cassini tried to measure the mass of Saturn's rings, and it turns out that they seem to have a mass of about half the mass of the Antarctic ice sheet. So if you took the Antarctic ice sheet, or half of it, I guess, smashed it up into small bits and then sprinkled it around Saturn, that's essentially what you're looking at. It's also about half the mass of Saturn's moon Mimas, which we can't see tonight. It's a bit too small. But it's the moon that looks a bit like the Death Star from Star Wars. Scientists are unsure when the rings of Saturn were formed. Some people have suggested that they've been there for billions of years. More recently, there's been the suggestion that they may only be something like 100 million years old. Now, you might think that sounds pretty old, but that's only a few % of the age of Saturn and the solar system. And this 100 million year estimate is based on estimates of how quickly they're losing mass. Again, we don't know exactly how they formed. Some people have suggested that it may have been from the disruption of a moon, and then slowly they're losing mass just due to interaction with the solar wind and radiation. Yeah, now, of course, Saturn's rings are a disk, and every now and then, as viewed from Earth, they actually disappear. So at the moment, they're tilted at quite a high inclination towards us, and so we can see the nice disk of Saturn's rings quite clearly. But every 13 to 15 years, they appear to disappear completely. And that's essentially when the Earth lines up with the plane of the disk of Saturn's rings. And then we're seeing them edge on. And as I said before, Saturn's rings are incredibly thin, so they completely disappear. It's not quite half of Saturn's orbital period. So Saturn orbits the Sun every 29.5 years. So roughly they disappear twice in every orbit of Saturn, but obviously it depends on exactly where the Earth is and so on as well. So it's every 13 or 15 years that they disappear. The next time that Saturn's rings will disappear will be in March 2025. So what's that? It's just over 4 years' time. But Saturn will actually be quite close to the Sun then, so it'll be hard to observe. And then the next time after that will be in 2038 and 2039. That will be what's actually known as a triple ring plane crossing. So that means that Earth, over the period of about 6 months, passes, well, the rings are viewed edge on, then they go slightly off edge on again, then back to edge on, slightly off edge on again, and then a third time they're viewed edge on. And that occurs in 2038 and 2039. So most of you are still around then, in about 18 years or so.
Here's Rhea.
Have a look at Saturn then.
Here's the
it will
moon,
just
Rhea.
look like a normal
Saturn.
planet with no rings at
Here.
all for a few weeks.
Here's Rhea.
How are we looking?
Right here. Where's Titan? Titan should be visible here.
One thing I would like to say,
Yes.
if I
So,
may.
hear from Stephen for a while.
It's hard.
Okay,
It's too tight.
go for it, Stephen.
It's actually
one
quite
thing
good.
that you can maybe see now is when you compare this image to the one that we had earlier, where you could see the moon Io very much closer to Jupiter, is that there is now actually a relatively clear distance between the two. And that is actually because the moon is moving. It is not stationary, it's moving around Jupiter. Like Matthew was saying, it's moving pretty fast. In, I think, 1.8 days, it's orbiting the planet. And this is fast enough that you can actually see it move. Now, a few days ago, we actually made a few images of Jupiter with its moons, as you can see now. This is taken half an hour apart, so these moons are moving pretty quickly.
Mm-hmm.
So that's fascinating to see. And I'm glad that we can actually see that live now.
Okay, so I'm just going to keep talking here because we do have this high altitude cloud coming across. Sam, could we have the image of Io, please? I'll talk a little bit about Jupiter's moons. Right, so Io, I'm not sure whether this is officially the case or not, but I always refer to Io as the pizza moon because I think it looks like a pizza. And so Io, as I mentioned before, this is the closest of the Galilean moons to Jupiter. It's the third largest, and it's the most volcanically active moon in the solar system. So you can see the yellowish colors here. Io has literally hundreds of volcanoes and lava flows that have been found on it from the various space probes that have investigated it. These volcanoes can be seen in some pictures taken by Galileo, and before that even Voyager back in the 70s. Anyway, when I was a kid, so there are actually NASA and ESA images of these volcanoes ejecting material into space, and some of that material is then trapped in Jupiter's powerful magnetic field, and actually rains down on the poles of Jupiter, producing the most dramatic aurora in the solar system. So you've probably heard of the aurora, where charged particles from the sun follow the magnetic field lines of the Earth and impact the atmosphere near the North Pole and the South Pole of the Earth. The same happens with Jupiter. Jupiter's got an even more powerful magnetic field, and particularly particles that are ejected from Io in the volcanoes get funneled along these magnetic field lines, hit into Jupiter's atmosphere, and produce aurora in Jupiter's atmosphere. So why is Io so volcanically active? That's because it's continuously heated by tidal forces from Jupiter. So Jupiter has a very strong gravitational field. Io has a slightly elliptical orbit, and that means it's continuously getting closer to Jupiter and then further away, and the change of the gravitational field from Jupiter distorts it. And then the other thing is you've got other moons there, such as Europa, which is the next moon out. That's helping to keep Io's orbit eccentric, and also, of course, there are tidal forces from Europa, Ganymede, and Callisto, although Callisto's a long way away. The next mission, which is going to do some close flybys of Io so that we'll get some more nice pictures, is NASA's Juno spacecraft, which is currently orbiting Jupiter, but it's scheduled to perhaps do some close flybys of Io in 2024. Now you might say, well, why don't they move Juno closer to Io sooner? 2024 is a long time to wait. But it turns out that Jupiter has very strong radiation belts. And this is, well, it's dangerous for space probes. It can damage their electronics. It's also, of course, dangerous to people. So it turns out that, yeah, people, I don't think will probably ever go to Io, or if they do, they'll have to be very well protected from the radiation. The next moon further out, maybe Sam, you could switch to Europa. Yeah, so you can see this image of Europa, again, taken from one of the space probes out to Jupiter. This is a very icy surface, all right? So this is the moon that you're currently looking at from Stephen's telescope view. We've got the two moons on the right of Jupiter. Io is the one that's very close to the surface of Jupiter. Europa is the one that's a little bit further out. This is the fourth largest moon of Jupiter, and it's thought that there's very strong evidence that it actually has an ice layer, and then underneath that there's an ocean. So it's believed to have a liquid water ocean beneath a layer of ice. There's still debate about how deep the layer of ice is. So some models have it somewhere between 10 and 30 kilometers thick. But some more recent models think that it might be a little bit shallower in places. And then below that ice sheet, the ocean is thought to be perhaps 100 kilometers deep. If that's the case, then the entire volume of liquid water on Europa would be something like 2 to 3 times the volume of Earth's oceans. So it's an awful lot of water that's potentially on Europa. And of course, the question is there any life in this water on Europa? That might be something that we can investigate with space probes in the future. There are 2 missions planned to investigate Europa over the next few years. One is the European Space Agency's JUICE mission, which is due to be launched in 2022. And then NASA also has a mission called Europa Clipper, which is due to be launched in 2025. And both of these will do some investigations of Europa. Unfortunately, no landers planned for Europa yet. So I mentioned about Jupiter's strong radiation. The radiation level at the surface of Europa is so strong that it would cause severe illness or death in a human being in just a single day. All right, so as I said, Europa's further away than Io, so the radiation at Io would kill you in less than a day, I guess. Don't know actually how fast you take to die if you have severe radiation poisoning. But anyway, let's not worry about that. Okay, so next moon out, this is now on the left-hand side of your image of Jupiter. As I mentioned, this is Ganymede, the largest moon in our solar system. It's 40% of Earth's radius in radius. So yeah, a little bit smaller than half the size of Earth. So it really is quite a large moon. It's 50% larger than our moon. And as I mentioned, slightly larger than the planet Mercury, but only about half the mass of the planet Mercury, because Mercury is particularly dense. Whereas Ganymede is sort of made up of a 50-50 mix of rock and water ice. Ganymede orbits Jupiter in almost exactly a week, about 7.2 days. So every week, if you come back, Ganymede will appear roughly in the same place. Europa is thought to have a subsurface ocean, and this is also true of Ganymede, although possibly not quite so extensive. Ganymede is also the only moon in the solar system to have a substantial magnetic field, although it's still about 100 times weaker than Earth's magnetic field. It's also the largest object in the solar system not to have a substantial atmosphere. Now, I mentioned about Galileo before, so he discovered the moons of Jupiter in January of 1610. That's 13 years before the last Great Conjunction that was as close as the one we're looking at right now. But it turns out that it's possible that there was a Chinese astronomer that observed Ganymede in 365 BC. His name was Daly, and there's a record of him observing a reddish object quite close to Jupiter with his naked eye. Now, it's not quite clear that this was Ganymede, because Ganymede doesn't really appear red. but it's possible that he might have seen this before Galileo discovered them with his telescope. You might be thinking, well, if Io and Europa are no good for humans, maybe we can go and live on Ganymede. So if you wanted to do this, then unfortunately the radiation's still a little bit strong there. The radiation would cause severe illness or death in human beings if you were there for about 2 months, which is probably a little bit too strong. So the best place probably to set up a base around Jupiter would be Callisto. So this is the furthest out of the Galilean moons. Has an orbital period of just over 2 weeks, 16.7 days. As I said, this has perhaps the oldest surface of any object in the solar system. There's no sign of geological activity, unlike Io with its volcanoes and Europa with its very young ice crust. It may also have a salty ocean, but again, the evidence is less clear than for Ganymede or Europa. But from the purposes of sending humans out to Jupiter, it orbits outside of Jupiter's main radiation belts. And so it's thought that the radiation level at Callisto's surface is only about 10 times higher than Earth's average background radiation. So this could allow a human base to be put there in the future. How are we going on the stream?
Cloud.
Okay, so the cloud has finally come, which is nice because I just finished talking about all of the moons. So I suggest we switch back to the studio now and possibly look at some of the footage we had from last night and also answer a few more questions. And we'll just keep the telescope running here to see whether that cloud is going to clear or not. So we'll switch back to the studio now.
Okay, wow. Firstly, Matthew, how do you know all that? Completely amazing. Gosh. Yeah, so many interesting things about those planets, about all those moons. So thank you ever so much for that. And really great to get some good looks at them all. So yeah, whether you have a telescope or not, I hope you all get the opportunity to see these beautiful planets for yourself at some point over the next few days. Stargazing is a really fantastic hobby, and now is a great time to observe the sky. With the sun setting so early, it's also a brilliant time to get children outside and finding their way around the sky. Another great object to look for at the moment is Mars, which is bright and fairly high up in the sky to the southeast at about 5-ish, so it's easy to spot, nice red colour. We've had a few questions in from some children. So Isaac, age 6 in Newcastle, has asked, would you be able to stand up on Jupiter or Saturn, or would you fall through them? And a similar question from Peter, who wants to know, do the gas giants have a solid core? So great questions from Isaac and Peter, and I'm going to put these ones to Nathan.
Hey, hopefully this time you can hear and see me. Apologies for the technical issues last time around, but that's a live stream. So just to say, the talk that we heard from Matthew about the different moons and planets, and these questions are really great to hear because they excite something in me I've had since I was young, this idea of being able to visit these amazing places. So to answer the questions we've had, you can't stand up on Jupiter and Saturn. They don't have a solid surface like the Earth with an atmosphere above it. Jupiter in particular, we weren't sure if it had a core, a sort of solid core in the middle or not. But recently, a mission called Juno that you've heard mentioned a few times, and you've seen some of the images from Juno, that started to show that it's got what's called a diffuse core. So a kind of core where there isn't any clear boundary between the atmosphere above and the sort of inner part, sort of mixed together. Now, the interesting thing about these two planets, as you go through the atmosphere, there's a lot of atmosphere. It's what we call deep, whereas Earth's atmosphere is quite shallow, really. The Earth is kind of about 6,000 kilometers of rock with maybe 100 kilometers of atmosphere, whereas Jupiter and Saturn, the atmosphere goes on and on and on. And in Jupiter in particular, as you go down, the pressure or the weight of the atmosphere above you is increasing, of course, the whole time. And once you get to a certain point, that can be as much as 40 million times the pressure you feel on Earth. And this can lead to something really interesting. We think perhaps a liquid metal version of hydrogen. So inside the core, there's a whole range of exciting physics happening that we sort of are beginning to understand, but there's lots more to learn. So hopefully with the missions that Matthew mentioned have gone there already, and more in the future, we'll learn more about these two beautiful objects. Back to Alice.
Brilliant, thank you, Nathan. We've also had a question from Archie, who's age 6, and he asks, how big is Jupiter's red spot?
Thanks, Archie. Legend. That's a fantastic question. Really, Jupiter's red spot is a really amazing feature, and it's really crazy to think that it's been there for probably hundreds of years. It's a very, what we call, stable feature. Now, it's so big, you could kind of pick Earth up and drop it into the Jupiter's red spot. It's about 1.5-ish times the width of Earth. It's essentially a huge storm. It doesn't have sort of, the wind speeds in the center are quite slow, but then as you move out, you can have sort of several hundred miles per hour winds. Now, the really interesting thing about the big red spot is it's kind of churning up the atmosphere of Jupiter. The clouds that you see, kind of ammonia and other things, they're in a very thin layer on the outside. Jupiter's red spot is a big storm that's churning material and bringing it up from deeper in the atmosphere of Jupiter. And as that comes up, it starts to interact with the light, or the ultraviolet light, and they change the color of what you can see in Jupiter's big red spot. It's a very dynamic feature, even though it's kind of been around for quite a long time. Thanks, Alice.
Wowee, Nathan, that's one big storm. Thank you very much for answering that. Now, believe it or not, astrophysicists don't spend all of their time looking through telescopes. In fact, for many of them, observing the stars is either a hobby or something they have to do with some serious bits of kit. So what on earth do astrophysicists spend all of their days doing in that case? So a few days, Alice actually had a really long discussion with Nathan to find out. I'm going to do that now.
So, silly question now. Do you have a favourite gas giant?
I guess my favourite sort of type of planets, more of a type rather than an individual one, are planets called hot Jupiters. And they were the first planets we've discovered orbiting a sun-like star. And they're really fascinating because they're just like Jupiter in many ways. They're really big, they're sort of these gas giants. But they're incredibly close to their parent star, closer even than Mercury is to the Sun. And there are all sorts of amazing things that happen. We find some of them where the atmosphere is just evaporating, essentially kind of boiling off. They're also rotating really slowly. They're what's called tidally locked, just like the Moon and the Earth. So the same face is always facing the star. There's a hot side and a cold side. And what this leads to is the jets on Jupiter, very similar situation, but this time they're huge. Rather than bands across Jupiter you'd see, if you could look at a hot Jupiter, you'd see just one big band. And that makes them really fascinating and quite kind of unique laboratories to understand how atmospheres work.
So what's your research specifically about?
I use models that are used to understand Earth's climate. So the UK Met Office uses a sort of big piece of software really that models the Earth's weather to give us weather prediction, but also the longer term changes in climate. And what we do here at Exeter is, as a large group of us, we've adapted that code and also kind of made our own pieces of software too, and tried to really model not so much the weather, but the kind of bulk climate, the average conditions that we might find on planets elsewhere. Now, that may sound a bit far-fetched, but we have quite a lot of observational information. So when planets, for example, move in between their star and us, some of the light comes through the atmosphere, and that can tell us things like the temperatures or what gases are in those atmospheres. And even in a couple of cases, we can actually get tentative measurements of the wind speed in these atmospheres. So there's quite a lot of information for us to use in our software to try and simulate what that climate might be like.
That's awesome. Sounds really cool. So for a lot of people, they probably can't imagine what a modern day astronomer actually does day to day. Can you give an idea what it actually means to be an astronomer?
Right now, spending a lot of time on Zoom calls. So given the current situation, there's a lot of communication. I guess the career as a whole, with research in particular, the really exciting part of it is you're constantly asking new questions and trying to understand things that we don't understand. That has its negative side. It makes you constantly feel a bit unintelligent, I guess, because you don't know the answer to the questions. But that tells me you're asking yourself the correct questions. Day to day, working in research is a lot about, at least in the way I do it, communicating with PhD students or masters and undergraduate students, and then people who work at a level called postdoctoral researchers, and working with them on the projects, either computer programming or working with telescopes to try and obtain data. So a lot of it is still actually sort of teamwork in a way, and working in larger teams to try to sort of answer these big questions. If you work at a university, that's also combined with, of course, teaching, which is really important, and really the research and the teaching are linked in many ways. And then, of course, sort of general jobs at the university to keep it running. So it's a very varied job, actually.
Okay, so in case you've just joined us, we are live streaming the Great Conjunction, the closest that Jupiter and Saturn have appeared in the sky for nearly 400 years, co-hosted by the University of Exeter Astrophysics Research Group and Exeter Science Centre. Time for an update on the view from Stephen and Matthew, and I think they're going to give us some pro tips about using telescopes yourselves. So over to you, Matthew and Stephen.
Right, okay, thanks very much, Natalie. Okay, so we don't have a view of Jupiter and Saturn at the moment. They're behind the bank of cloud, but we're still just waiting to see whether that clears. Somebody has asked, though, why we're using a portable telescope that was set up on the roof of the physics building, because we actually have a telescope which is permanently fixed on the roof of the physics building, which we use for teaching our students here. And so the question is, why don't we use that one, which is much larger and more powerful than the portable one that Stephen owns? And the reason is just simply due to the orientation of the physics building. It turns out that whoever built the physics building here back in 1966, I think it was, or was it 1968? Something like that anyway. They must have, I don't know, had ancestors who worked on Stonehenge or something, because they aligned the physics building absolutely perfectly in the southwest northeast direction. Now, the physics building at Exeter has a two-story high, very long rectangular block, and then at one end it's got a tower which is about 7 stories high. Now, our permanent telescope is on the 2-story high slab block, as we called it, but it's on the northeast side of the tower. And as you know, in order to see the Great Conjunction yourself, you need a good view of the southwestern horizon. Unfortunately, our 7-story high tower completely blocks the view of Jupiter and Saturn from our permanently mounted telescope on the roof of the physics building. And so we've had to actually set up this portable telescope on the southwest side of the tower, which involves climbing over large concrete blocks and air conditioning systems. And yesterday we were wading around in water here after a strong rain shower. So yes, that's essentially the reason why we're using this portable telescope. It's the only place on the physics building where we could actually view Jupiter and Saturn. So I hope that answers that question. In terms of tips for observing yourself, I'm not quite sure what I can say there. One thing you might consider doing if you're a teenager is, when I was a teenager in New Zealand, I'm from the North Island of New Zealand originally, and my father and I, we built our own telescope. Again, it was a Newtonian telescope, like the one that Stephen's got here tonight. We actually bought the mirrors ourselves, but then built the rest of it ourselves. That was just using a simple Dobsonian mount. I've remembered the name of it now, which is not as useful as an equatorial mount, because it doesn't allow you to track the motion of the stars across the sky. But it's relatively easy to build. So possibly you could think about building your own telescope. It's obviously, you can buy them as well, but it's a good project if you wanted to build your own. The one I have at home in New Zealand is a 10-inch, so it's quite a large one. But yeah, in order to get started in astronomy,
There's
I'd say
nothing
you
like
probably
building your own
want,
telescope.
ideally,
All my
something
telescopes
like
I've built
5 or
myself
6 inch,
from the mirror to the telescope. It's when you can see the sky and the universe with the telescope that you made yourself. It is an extra dimension of satisfaction and appreciation of the universe and of what you're capable of doing. So it's really quite a nice experience to build your own telescope. Here at Astronomy for Change, we're going to be running classes and programs about producing your own telescope mirrors and ultimately completing a telescope, a full telescope, usable telescope that you can see the universe around you with something made by your own hands.
She has a project studying light pollution, which is going to happen over the next couple of years.
Nice view of Jupiter now. You can see
the moon and the planets, or at least
Callisto is all the way to the left.
Bright planets.
Go to Stellarium.
Are easily visible here, even from light polluted cities, but you won't view the fainter objects from
Callisto, Ganymede. There's a star here. That's a star.
Yeah, and
Callisto, Ganymede,
as I said in one of my
Io,
videos,
and Europa
in terms of the
on
Great
other side.
Conjunction,
So this is
if you
what
have
we see here.
a clear night over the next few days,
Callisto,
binoculars
Ganymede.
are also
Yes,
good
this is a
for
star.
viewing it. If
Here's
you have
Callisto.
binoculars with
Here's
a
Ganymede. Here's
magnification of
Io and
greater
Europa.
than about 8 times, and then
Callisto,
you should
Ganymede,
be able to see
Io,
some
and
of the
Europa.
Galilean moons that we've been looking at tonight, even through a pair of binoculars. I think I'll switch back to
That's a good view.
the
It's
studio
quite
again,
good.
and they can maybe answer
The moons are
questions.
presented quite
Okay,
nice.
Andy, back to you now.
See how low his telescope is pointing towards the horizon?
Okay, so
You get
we've
a
been
sense
so
of
lucky having some clear patches of sky tonight, and for those of you who've been following the lead up to this event, you'll know that it was very weather dependent, and we were obviously rained out yesterday. So Exeter is widely recognised as a global centre for climate science research, being home both to the University of Exeter and the Met Office, with some fantastic collaborations between the teams of scientists.
And believe it or not, we can learn a lot about the weather on other planets, including Jupiter and Saturn, by taking models that scientists have made of the Earth's climate and adapting them for use with other planets. And a few weeks ago, I spoke to Dr. Stephen Thompson about his research doing just this.
So we're very familiar with the weather on Earth, but what is Jupiter's weather like?
That's a great question, thank you. So I guess Jupiter's weather has a lot of familiar features. You know, if you went there, I mean, it wouldn't be advised, but if you went there, you'd recognise a lot of things, right? So Jupiter's atmosphere is full of storms, it's full of lightning, full of clouds and waves and all this sort of stuff that we'd be familiar with. But Jupiter's most significant weather feature, perhaps, is its jet streams. And jet streams are these things that are like rivers of air that run in the atmosphere. On Jupiter, they run almost perfectly west to east and east to west. Which is quite interesting. They're sort of interestingly straight compared to those on Earth, which sort of meander a lot. Now on Earth we have sort of 2 jet streams per hemisphere, and they play a big role in the weather that happens all over the world, including here in the UK. But Jupiter's jet streams are much more numerous and powerful, so it has roughly 8 jet streams per hemisphere compared to Earth's 2. But they can also, on Jupiter, reach speeds of up to 150 meters a second or 330 miles per hour, so much, much faster than we find here on Earth, and therefore much more extreme in lots of ways.
I'm wondering about Saturn. So we've heard quite a lot about Jupiter, and of course Jupiter's kind of a big gas giant that we use as a model for other exoplanets. But how is Saturn different?
Well, in terms of their atmospheres, Jupiter and Saturn are very similar and have many similarities. They're both made of predominantly hydrogen, and they're both gas giants. The fact that they're predominantly hydrogen sort of relates to their sort of common formation from the solar nebula, which is mostly sort of hydrogen and things like that. They both have multiple jet streams and clouds of different kinds. But one thing you might notice if you look at Saturn and you sort of forget about the beautiful rings for a moment, if you just look at Saturn as a planet, it doesn't have these sort of beautiful stripes or striking colours that Jupiter has. And that's partly just because Saturn is covered in a sort of chemical haze that makes it much more difficult to see down to the cloud level. So if you sort of get rid of that, you can see more similar features to Jupiter, but just in terms of looking at them perhaps through a telescope, powerful telescope at least, that's one of the big reasons, is that the haze is there on Saturn, whereas much less present on Jupiter.
So what is your research specifically about?
Well, that's a question I think about the answer to every day. It's a good thing to make sure that you pin down. I count myself very lucky to be in a job where I can think about all sorts of things, but my main goal as a researcher really is to understand what makes the planets different from each other, and how we can sort of use that understanding to understand perhaps Earth's climate better. So, for example, why does Jupiter have more jet streams than Saturn or Uranus and Neptune? What powers the jet streams on those different planets? Is it the same process? Is it a different process? All that sort of thing. We mentioned earlier about what makes the jet streams on Jupiter so straight, whereas on Earth they're much more wavy. And these are the kind of questions that I like to think about. Now, obviously, I don't just sit there in a darkened room thinking about it. How do I actually go about studying this? And well, I mainly do this by designing and running experiments with numerical models of atmospheres known as general circulation models, or GCMs for short. So, for example, by taking that code, what I can do is I can change different things about a planet, right? I can make it larger, I can spin it faster, and I can see how that changes its weather and its jet streams and its storms. And I can also do the same sort of thing with like similar codes to problems in climate science, right? I could say, well, how do the jet streams change under climate change? So I could change the CO2 level, change aerosol levels, and have a look at how the dynamics changes. And as I said, I count myself very lucky to be able to think about these things as my job.
Okay, and we're going to pass directly to Matthew because we've got some brilliant images to show you.
Okay, so welcome back to the telescope. So yeah, Jupiter and Saturn are getting very low now. We just wanted to come back just before we lose them completely to mention that if you look now to the right of Jupiter again, you can clearly see Europa a little bit further away, and then Io between Europa and Jupiter. And as I mentioned before, Io orbits Jupiter in just 1.8 days. And so just while we've been live streaming over the last hour or so, Io has actually moved significantly away from Jupiter's limb, right? So you'll remember when we first started looking at Jupiter and we first saw the moons, we could clearly see Europa separated from Jupiter, but Io itself was just sort of merging into the edge of Jupiter's surface. But over the last hour, it's moved appreciably and is now roughly halfway between halfway between Europa and Jupiter itself. So we just wanted to point that out. They're getting very low in the sky now. I'd say less than 5 degrees above the horizon. So we are going to lose them in the near future. But hopefully you've really enjoyed the images that we've been able to show you tonight. And stay tuned, because we still have images to show you from last night in the coming few minutes. All right, so I'm going to hand back to the studio again now.
Thanks very much, Matthew. It's been fantastic to see these images, just as we can make the most of them before they go. So a few moments ago, we saw my interview with Stephen, and I've got a brilliant question for you, Stephen, from the YouTube chat. Now, this one's from Elfwald, who asks, is there a hexagonal electrical storm at one of Saturn's poles? If you can answer that for us, please.
Thanks very much, Natalie. Yeah, it's a great question. So yes, indeed, on Saturn we do see a fascinating hexagonal pattern at the North Pole, which we refer to very imaginatively as the North Pole, a hexagon. And it's visualized through a sort of hexagonal pattern in Saturn's clouds. Now we do see something like this storm in Saturn's aurora, so there is an electrical component, but it's observed clearest in the cloud bands. So the hexagonal part is perhaps more of a conventional storm rather than an electrical storm. Now, as Matthew mentioned earlier, both Jupiter and Saturn have numerous jet streams, which are like rivers of air in the atmosphere. Now, on Jupiter, if you picture those stripes, which we've seen through the telescope tonight, they're very straight, right? They run more or less straight across the planet. But on Saturn, as your question alludes to, one of the jet streams near the pole has 6 very distinct sides. It's almost a perfect hexagon. I mean, it's puzzled scientists for a great many years where that hexagon comes from. Now, one idea is that it's very much like a standing wave, perhaps like a wave on a guitar string. You've got a guitar string that has these components, a little bit like that, where the string is tied to itself at the end. Another idea, perhaps, is that it's related to fluid motion deep in Saturn's atmosphere. So Saturn's atmosphere, or planets like Saturn, are very hot in the middle and cooler in the outer layers, and this generates something that we refer to as convection. And convection can produce very interesting polygonal shapes, a little bit like what you might see in a kitchen if you heat up some butter or sugar in a pan. And one idea is that the storms that are generated by convection deep in the atmosphere create this fantastic hexagonal pattern in the outer atmosphere. But we're still very much exploring this phenomenon, so for all those budding scientists out there, there's plenty still for you to explore, and we very much encourage you to consider looking at physics and maths in the future.
Thanks so much, Stephen. That was a great answer. So we've got a few more questions now. As many of you might know, there is a large belt of asteroids orbiting the Sun between Mars and Jupiter in the solar system. Chris wants to know, why don't asteroids obscure the view of Jupiter and Saturn? I'm going to ask Federica to answer this one for us.
Well, that's quite an interesting question. Okay, Jupiter and Saturn are the biggest non-stellar bodies of our solar system. Even at their large distance from Earth, they'll still have a significant resolvable size in the sky. For an eclipse to occur, we would need to either have a substantially large asteroid or an asteroid orbiting very close to Earth. Most asteroids in the solar system are located in two belts, the closest to us being between Mars and Jupiter. The total mass of the asteroid composing the main belt is approximately only 4% the mass of the Moon, as in our Moon, meaning that most of the asteroids in the belt are pretty small. Combining these two facts, the small size of the asteroid and their significant distance from Earth do not allow them to be large enough to completely eclipse large planets like Jupiter and Saturn. So unfortunately, no eclipsing from asteroids.
Thank you. We've had a few questions from school children, and Fede produced a fantastic video for children, so please do check that out on the JupiterSaturn2020.org website. And we've got another one here. So Caleb, aged 8 from Barnstable, has asked, when will people be able to orbit Jupiter and Saturn? Fede, can you answer Caleb's question?
Yeah, okay, so the first time we were able to send something as far as Jupiter, it was all the way back in 1973. Since then, we sent various probes to the two planets to see how they look close up. Juno and Cassini have been mentioned before in the live. However, sending people to Jupiter and Saturn will definitely take a bit longer. The travel itself is not the difficult part. However, there are two big issues. First of all, it is very dangerous for people to be close to these planets, since their radiation fields are very strong and would be very difficult to survive. And even if we did build a super sturdy spacecraft with incredibly good spacesuits, it's still very difficult because with the current rockets, the journey will take several years, and we wouldn't be able to go there and back. It's gonna take a bit longer, so unless we want our astronauts to go there and stay there for the rest of their lives, we still need a couple more years. And the development of nuclear-powered rockets, it's probably going to take a bit longer. So people better stay around Earth and maybe visit Mars first.
Great, thank you so much for that answer. That was great. So we're now going to watch a video that Matthew made earlier, which takes a look at some of the footage they got last night and comparing it to today. So yeah, we'll go to that, please.
Yesterday we abandoned our live stream after about 20 minutes due to thick cloud and rain. However, about 30 minutes after we stopped streaming, the sky cleared for about half an hour. I took this photo of Jupiter and Saturn over Exeter then. You can see they're much closer together than they were in mid-December. But what else have we got to show you? If you tuned in last night, you'll remember that we hoped to see something like this. We thought we'd be able to see Saturn's rings and 3 of the Galilean moons of Jupiter. Jupiter's closest large moon, Io, was behind Jupiter last night. We also hoped to be able to see Saturn's largest moon, Titan. Jupiter and Saturn were separated by half the diameter of Earth's moon last night. This is what we saw through the telescope. Here we've used a low sensitivity setting so that you can see the rings of Saturn and even some of the cloud bands in Jupiter's rapidly rotating atmosphere. The three Galilean moons, Callisto, Ganymede and Europa, can also be seen faintly with this low sensitivity setting, but they're exactly where they should be. Stephen made this photo last night by adding together several individual photos. Here you see some of the video footage that we took last night. The atmosphere was reasonably still last night, given the changeable weather. Hopefully we'll see something similar tonight. By increasing the sensitivity of the CCD camera on the telescope, we can see much fainter objects, but Jupiter and Saturn themselves become overexposed. Here we're trying to see as many moons as we can, and it was more than we imagined. There are 7 moons in this photo, 3 of Jupiter's and 4 of Saturn's. Saturn's largest moon, Titan, the second largest, Rhea, and its 4th and 5th largest moons, Dione and Tethys. What an incredible sight.
This was yesterday.
Here again is the video footage of Jupiter, Saturn, and the 7 moons.
It's Titan.
Here you can clearly see Jupiter's large moons and Titan, but Rhea, Dione, and Tethys are more difficult to see. Finally, last night Earth's moon was also in the sky, not too far away from Jupiter and Saturn. Here is another photo I took of the sky over Exeter last night. You can see the moon on the left and Jupiter and Saturn low on the right. Meanwhile, Stephen was using his telescope to explore the craters of the moon. Earth's moon really is amazing to explore using binoculars or a small telescope. The best phases of the
This is something we're going to be doing very soon here at Astronomy for Change. Live streaming our own events.
Between day and night, because
our
the
own
long
observing
shadows
sessions, our own
allow
observing
you to
events,
see depths
probably once a week.
craters.
That's coming up
We
soon.
probably won't see the moon again tonight, but hopefully we'll see Jupiter and Saturn again, but this time even closer together.
Great, thank you. So we now have some more questions now about the solar system. Andrew wants to know why all the planets rotate in the same direction, and Ayan wants to know why they are all roughly in the same plane as each other. Why don't collisions cause them to go off in random directions? So Sebastian, can we hear from you on these ones, please?
Yeah, sure. Great questions, great questions. Indeed, if you look at the solar system, one of the first things you'll notice is that all the planets go around the sun in pretty circular orbits. They're all pretty much in the same plane, and they all orbit in the same direction. And the reason for this has to do with their formation. So when the solar system formed 4.5 billion years ago, the sun was surrounded by this big, pretty flat disk of gas and dust. You can think of it like a giant pancake or a donut, but made of gas and rotating. And the planetary building blocks and ultimately the planets formed from that disk, and so in a way they inherited the rotation. And that's why they're all going around the sun in the same plane, in the same direction. Now, it's true, collisions and gravitational interactions did stir things up a little bit, but at least in the solar system, not by too much, and so all the planets are within a few degrees of each other. This is not true, by the way, for smaller bodies like comets and asteroids or Kuiper Belt objects. These are less massive, and this means that the planets could sort of throw them around, kick them about quite easily, and most of these have very inclined orbits, which means they spend quite a lot of time away from the plane where all the planets are. Back to you.
Great, thank you, Sebastian. Okay, so now, if you've just tuned in, we're still live streaming the Great Conjunction from the University of Exeter Physics Building. This is the closest that Jupiter and Saturn have appeared in the sky for 400 years. We're going to pop back now to Matthew and Stephen at the telescope.
Oh, interesting.
Okay. All right, so we just thought you might like to see, so Chris Brunt, who made a very brief appearance yesterday, has set up a low light camera, which you're now looking at, and that's the green image, the green round image. And we've also got an infrared camera here, and it is quite cold tonight. You can see the sky is very dark, for example. My head, believe it or not, is still actually quite warm. That's why it's glowing orange. This is down in the lower left of your screens. And then in the low light camera, that's the green image, you can see here, this is the moon, all right? So that's the moon in the sky, and then obviously we've got the top of the physics building here. But yeah, we just thought you might like to see. Somebody asked last night whether we could use an infrared camera perhaps to look through the cloud and to see Jupiter and Saturn when we couldn't see them because of the cloud. We can't use an infrared camera to look through the cloud. We could use radio. Chris talked a little bit about that last night. But yeah, we just thought you might like to see our infrared and low light cameras here as well. But we're going to switch back to the telescope now, Sam, and we're going to show you a view of the moon. So again, this is
nice.
From Stephen's telescope, and what you can see here is some craters on the
moon's a waxing crescent, and it's approaching first quarter. Tomorrow begins first quarter moon.
One of the things which
and 2
is
weeks
great
from
to
that
look
is
at
full
through a
moon.
telescope,
So.
Even a small telescope or even a pair of binoculars, is the moon, and in particular exploring all of the craters that are on the moon. And as I said in the video, which I think you just saw recently, the best way to observe the craters is actually when they're close to the terminator. So that's the where the day is passing into night.
Same time. We have a brief interruption in the internet, it seems. The signal coming from the UK.
Because that's where the shadows that are cast by mountains or the edges of the crater walls are the longest, and so you can actually get a sense of the three-dimensional perspective from the craters. Stephen, do you want to sort of, just scroll across the moon's face? So that the moon at the moment relatively close to the sun, so it's quite a strong crescent.
Waxing crescent.
And so just as Stephen scrolls across the surface of the moon here, you can see some of the craters, impact craters left by asteroids and comets hitting it. And then you see the flat regions. These are younger surfaces where they've been filled up by lava, I believe, from molten material. But a long time ago. It's not like Io, there's no active volcanoes on our moon anymore.
The moon is considered what they call a dead world.
Yes, you can see some
There's no more
really
activity,
quite large craters. You'll see some of the
These
craters
are the mare.
have
The mare
mountains
are
right in the middle
younger
of them.
regions of
This is due to when
magma
a large
and lava
object
that came up through impact craters.
The moon,
the magma came up through a breach in the surface and then filled out the region, the plain in the surrounding area. It's newer material,
so
it's
we
newer
thought
regions.
you might
So
like to see a few more
the craters are a good way to
of the moon.
get a sense of
As
the
I said,
age
if you've
of
got
a
your own
particular
small
region.
telescope, the moon's always a wonderful object to look at. You don't have to worry about it being faint. You can see it fine from a light polluted city.
It's a very good, very good image. The mountains and valleys right here.
So I think we'll pass back to the studio now. So see you guys later.
Thanks very much, Matthew. Fantastic. It's great to see the moon so up close. Now we're going to take a few more questions from you now. We've got a question from Luke, aged 8, in Newcastle. If there was life on Jupiter, what would it look like? I think this is a really good one for Federica. Fede, can you answer this one?
Yeah. Okay, so any alien life on Jupiter would be extremely different from us or anything we might be familiar
Would
with.
have to exist in the clouds.
So definitely no green or gray aliens like
There's
also
no
sci-fi
solid
movies
surface on
try to
Jupiter.
tell
It's
us.
just
First and foremost,
it's got
since there is no solid surface on
Thank you.
Jupiter, any life form would need to be able to evolve by floating in the dense clouds we see from space. These clouds are actually so thick that the Juno spacecraft orbiting around Jupiter is still trying to look inside. Moreover, the temperature in these clouds are about minus 145 degrees Celsius, which is much, much colder than anything anywhere on the surface of Earth. So definitely no water-based life. Finally, there's also no oxygen as we know it in Jupiter's atmosphere, only hydrogen and helium gases. So aliens definitely wouldn't breathe like us. We would need a lot more information to actually figure out a shape, what they would look like. But at the moment, it's still science fiction.
Thanks, Fede. So if there was life on Jupiter, it would look
wouldn't be on
like
Jupiter, it would
we
be in the
have
cloud
here on
bands,
Earth.
the atmosphere of
Now,
Jupiter.
we've had quite a few people asking for advice on what kind of telescopes would be best for a beginner interested in viewing planets and their moons. So let's hand back to Matthew and Stephen. Perhaps they can answer this one at the telescope and let us know what they think.
Yeah, okay, great. So for a beginner, well, I don't know, my first telescope was quite a small one. I think it was about a 3-inch refractor, so that's using lenses rather than mirrors. Personally, I always find them a bit disappointing. I think really you want at least, I'd say, a 5-inch reflector. Again, it doesn't have to be fancy, a simple
The standard size is 6-inch or 15 centimeters. 4.5 or 6-inch, which is
I have no idea
12 centimeters or 15 centimeter reflecting telescope
to be honest, I
ideal.
personally wouldn't buy anything smaller than that.
Yeah, he's correct. It is disappointing for anything smaller.
You know, for a
There's
very
certain
small
level of
telescope,
certain
you'd be able to see
expectation.
the moon, okay, you'd be able to see
There's certain expectations which are not met by a smaller telescope, and once you look through it, you become disappointed and you lose interest. So the best investment would be a 20 centimeter reflecting telescope, a Newtonian reflecting telescope.
The higher the resolution you're going to get. But then, probably more importantly, is the light gathering
Yes,
power.
he's correct
So
with
again,
that also.
The larger the mirror or the main lens, the more light that you're getting in.
And the finer the resolution as well.
If you want to go to high magnification, for example, because as you magnify an image, say, of a planet more and more, then the surface brightness, the brightness of the object that you're looking at, gets fainter and fainter the more you magnify it. And so if you want to go to a reasonably high magnification, you need to have a lot of light coming into your telescope to do that. Otherwise, it just gets too faint. Yeah, personally, I think 5 or 6 inch.
You can't get a 5-inch. None that I've seen. The standard size is 6-inch.
Hopefully that answers the question. In terms of binoculars,
9 by 63, 10 by 70, 10 by 80, 12 by 80. I have a 9 by 63 and a 10 by 80.
The
excellent
diameter of the binocular lenses, the main lenses, shouldn't be less than about 2 inches, so 50
which is 50 millimeters.
So anything from 50 millimeters or greater would be good for astronomical purposes. Again, with binoculars, you've got the question of weight. All right, so obviously larger lenses are going to give you more light, but if they become too heavy, then especially for children, they're going to be very difficult to hold, and you may then end up having to put them on a tripod. Similarly, you might think more magnification is better as well, but again, more magnification just means that if you're moving the binoculars around a little bit, then your image is going to be moving, and it's hard to hold them still. So something like 8 by 50, so 8 times magnification and 50
I've never seen an 8 by 50.
lenses,
It's 10 by 50.
is a good sort of size. It's a good
9 by
compromise
63 is,
between light
I have a
gathering
pair of
power,
9 by 63 and a pair of 10 by
being
80s.
able to actually hold
10 by
it.
80s you should use a tripod.
But yeah, you could go up to
The 9 by
like
63
10
is
by
very good.
60s,
It's ideal.
Maybe 12
Isn't it? We
by
have another
60,
image of the
12
moon.
by 80.
You can see the turbulent atmosphere and light passage of the passage of some light clouds.
And terrestrial pursuits as well, such as bird watching and so on. Yeah, the other thing to be a bit aware of with binoculars, I guess, is probably don't buy ones that are sort of too cheap. You might be better to spend a little bit more on good quality optics, but actually just have a little bit smaller diameter, because you want some decent optics as well. I hope that's of some help.
We're going to be offering
back to
telescope making programs here at Astronomy for
Thanks,
Change
Matthew.
coming up in the spring.
A great answer. Thank you very much. So we are nearly at an end, but we have had a really interesting question submitted to us from Michael. Do Jupiter and Saturn change their relative orbital speed around the Sun because of their mutual gravitational attraction as they get closer to each other during the Great Conjunction?
Very
great question.
slightly.
Perhaps Jenny
Yes.
could answer this for us?
Yes, I can answer this one. This is a really good question. So Jupiter's going around the Sun at 13 kilometers per second. And Saturn is going around the Sun at about 10 kilometers per second. So as I said,
The Earth is 30
further
kilometers
out
per
in the
second.
solar system, they travel more slowly. But that speed is basically set by the Sun, which is 1,000 times more massive than Jupiter.
But it's much
but
further
in fact,
away.
Jupiter and Saturn pull on each other all the time, and they do have a small influence on each other's
Exactly.
speed. So as Jupiter comes up and towards overtaking Saturn, it will pull Saturn backwards a bit.
Yeah, it'll
and
slow
as
it down.
Jupiter overtakes Saturn, Saturn will then speed up to
This
try
was
and
the
keep
same
up
dynamic
with
that allowed us
Jupiter.
to discover the
But this is a
location
really
and the
small
existence of the planet Neptune.
So this
1865.
so remember, when Jupiter and Saturn are in conjunction, they're still 4.4 times the Earth-Sun distance away from each other. So they're still very far apart. So the speed difference due to one going past each other is just about a few meters per second compared to 10 kilometers per second for Jupiter. So that's less than 0.1% speed difference.
Yes, but it's reasonable.
Thanks, Jenny. That's
given
fantastic.
the distances.
I think that's about all we've got time for today. So we're going to go to Matthew and Stephen for one final look through the telescope. And we have just one more question to Matthew while we're passing over there. Matthew, Robert would like to know about the next Great Conjunction. Will the Great
60
Conjunction
years
of
hence.
2080 be higher in the sky than tonight? Over to you, Matthew.
Yeah, great.
With
Okay,
stellarium,
thanks
we
very
can
much.
answer that.
So we've got another development here. Stephen has just managed to find Neptune.
Oh, brilliant.
While he's finding that, I'll answer your question. And Sam is going to switch to the stream, I think.
Yeah, Neptune.
Can you look at there? Excellent. Okay, so
Neptune.
while I'm answering the question, you can all enjoy looking at Neptune. Neptune, of course, well, since Pluto got demoted to a dwarf planet, Neptune is now the most distant planet in the solar system. And I haven't brushed up on my knowledge of Neptune, but it's somewhere around
It's setting. Jupiter and
17
Saturn are
times
setting.
the mass of the Earth, plus
See if we
and
can
minus a
find
little bit.
Neptune.
But anyway, it's also a beautiful sort of bluish color. Anyway, what was the question? Right, okay, the 2080, yes, okay, so in 60 years' time, we do this all over again. And so Natalie will be a little bit older, and Frederica might still be alive. And yeah, you might have to get someone to replace me. But anyway, so in 2080, the conjunction then is going to be almost exactly as close as this one. But it's going to be easier to observe.
The tiny disk of Neptune.
So I believe it's going to be something like 40 degrees above the horizon, rather than 15 degrees above the horizon when it first becomes visible in the twilight, as we have at the moment. So it will be a lot easier to observe, but you're going to have to wait 60 years in order to see that. Yeah, I've got an 11-year-old son, so I guess he'll be 71, so he might get to see it, but I'm not sure I'll still be around then. So yeah, easier to observe, but you're going to have to wait 60 years. How are we going on the viewing, Stephen? Yeah, so this is Neptune. Of course, Neptune's a long, long way away.
30 astronomical units.
And so you're just going to be seeing a very small...
30 times the distance from the Earth to the Sun, to Neptune.
But it's not too impressive.
From us, it's 29.
Yeah, but it's not too impressive, exactly. Yeah, so I think that's an extra bonus for you all tonight.
Yeah,
you also get to see Neptune
good.
as well. We'll pass back to the studio now, I think.
It's 6:22 in the UK, in Exeter.
Fantastic. Thank you very much, Matthew, and Stephen over there as well. Well done for finding Neptune. So we hope you've enjoyed this live stream event where we've had a fantastic and rare view of Jupiter and Saturn in the same field of view of a single telescope, as well as some of their moons and our moon and Neptune. So we've had some fantastic discussions as well with our experts. Thank you all so much for taking part, and we've really enjoyed answering all of your questions.
Okay, this
event was brought to you by the University of Exeter's Astrophysics Group in conjunction with the Exeter Science Centre. You can find more resources on the conjunction event by visiting jupitersaturn2020.org. And you can also find out about what Natalie, I and the team are planning for the Exeter Science Centre by visiting our website, exetersciencecentre.org.
Thank you so much to everyone involved tonight. We'll provide the footage of this live event on the jupitersaturn2020.org website, along with lots of videos and resources about the Great Conjunction. Thank you all for watching. We hope you have time for some stargazing over the holidays. Take care and Merry Christmas.
Okay, this is Dr. Jim Daly. This was a live stream event from the University of Exeter, the Great Conjunction 2020. Our presenters, Dr. Alice Mills, Dr. Natalie Whitehead, Dr. Stephen Ryder, Professor Matthew Bate, and others. This is Dr. Jim Daly at Astronomy for Change. I hope everybody enjoyed this video, this live stream event. And we're going to be doing more of these come the spring with our own telescope and our own live stream events. This was brought to you courtesy of the University of Exeter in England, UK. And for all of us here at Astronomy for Change, stay well and keep looking up. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and choose a membership level suitable for you. Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Membership is free at Astronomy for Change. Choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.